Alright, now we're going to be talking about another type of op-amp circuit that is very common, and it is called the Adder Amplifier or the voltage adder. It has many different names, so essentially what it does is it takes in multiple input voltages and then it just adds them together to contribute to the total gain of the amplifier. So this is a basic setting in which you have 3 voltages, but you can have any number you want. The principles are pretty much the same. And essentially one of the terminals you want to connect them to ground. That's basically the main principle that we're going to be using over here. So we want to find an expression V0 in terms of all the input voltages. So we're going to apply our ideal op-amp rules to see if we can derive an expression. First thing we notice is that we're connected here to ground, which means that the voltage over here is going to be 0 volts. And we know that the potential at both terminals in an ideal op-amp should be the same. So that means the voltage at this node is also going to be 0 volts. And because this node and that node are essentially the same, because they're just connected through a wire, that's also going to be 0 volts. So that's really important, because what that does is that it allows us to calculate the current flowing through each of these resistors. So namely I1, then I2, and finally I3. Okay? So in this case, we have I1 is simply going to be V1 minus 0, which is V1 divided by the resistance 1. Then I2 is going to be equal to V2 divided by R2. And then I3 is equal to V3 divided by R3. And so on and so forth. And then what we're going to have over here is, well, we have some current coming out of that. So at this node, if we look at it very carefully, we have 3 currents coming in. We have I1, I2, and I3. So we can apply KCL at this node, and we know that I should be equal to the sum of the other currents coming in. Okay, so we know what this is going to be. Now the next thing is, at this other node, we're going to have I coming in. We have a connection to a terminal, but ideal op-amp rule says that the op-amp does not draw any current. So any current coming into the terminal is going to be 0, which means that whatever current comes out into the load resistance, or RL in this case, it's also going to be equal to that. So KCL at this node over here tells you that I is just going to come straight through. So that means that now the current through this resistor is just going to be that. And now I through RL, which is just going to be equal to I, is going to be equal to 0 minus V0 divided by RL, which is just minus V0 over RL. Alright, and then we're going to have a bunch of other things. So the first thing is, well, we know what this is. This whole thing here is going to be equal to the sum of all these things. So this current over here is going to be that. So we're going to have V1 over R1 plus V2 over R2 plus V3 over R3. Okay. And then the last thing is going to be, well, we're just going to have V0, and this is going to be our expression in terms of the input voltages, and that's going to be equal to minus RL times V1 over R1 plus V2 over R2 plus V3 over R3. And there are a few special cases of this. So in the case where all the resistors are the same, and let's call that RG, then V0 would simply be minus RL over RG times the sum of the voltages, or the voltage inputs. And we can generalize this even further, and we could have something that looks a little bit like this. So imagine we have a bunch of different inputs, V1, V2, and so on, all the way to Vn, all coming in at this terminal, minus plus, then this is connected to ground, and then we have the output voltage over here, and then we also have a resistance load, or essentially just an RL over here. Then considering that each of these is going to have some resistance, R1, R2, and so forth, then the total output voltage out of that circuit is going to be minus RL times the sum of the voltages divided by each resistance. And that's going to be, this is basically what we call it, the voltage adder, because we're essentially adding each of those voltage or potential inputs. And you notice that one of the characteristics of this type of amplifier is that the output is also inverted. So that means that the signal is basically going to flip around because it is negative. But it is a very important thing, and we're actually going to make use of this in later videos. It's a very, very neat way of performing addition of input signals. So if you imagine the way that a calculator would normally add numbers together in a digital way, this is kind of how you would add things in an analog way by using resistors and all those types of components.